Hello everyone, this is Rebecca Arvin with the Water Environment Federation. I want to welcome each of you to the Process Control for Activated Sludge webcast with WEF's past president, Jeanette Brown. Before we begin, I would like to quickly review a few logistics. All of the PDF PowerPoint presentations are available for downloading at WEF's STP link. This link was distributed via email yesterday and will be distributed again tomorrow for anyone that registered after the time of distribution. The FTP link for this webcast also has information on how to receive professional development hours for those eligible to receive these training credits. There are 2 PDH credits for this webcast. You will need to complete the evaluation form to receive the PDH certificate. Your feedback on this webcast is important and helps identify future webcast topics that are timely and helpful to you. Please follow the PDH instructions and check with your state accreditation agency on how to receive this credit. During this webcast, while you cannot speak directly to Jeanette, you will, however, have an opportunity to submit questions by typing in your specific question via the question box that appears on your PC. I will be accumulating questions and direct them to Jeanette at the end of the webcast. We will be recording this webcast. A link will be sent to all registered users tomorrow so that you can share it with colleagues who could not attend the webcast. If you have any additional questions after the webcast has ended, please email webcast with an S at wef.org. Before we get started, I have a poll question for everyone. Let me go ahead and launch it. Now the question is, how many people are participating in the webcast today at your computer? If you're participating by yourself, please respond 1. If you're participating in a conference room, for example, or have several people gathered around your computer, just do a quick head count. And we also got a question from Dawn about CEUs for the webcast. There are PDHs available that you can claim by completing the evaluation form. Your state might accept these as CEUs, but they're primarily PDHs. So it looks like everyone has voted. So I'll go ahead and share those results. Looks like we have 80% as 1, but several people with 2 to 4 and 5 to 10. I'd like to thank Jeanette for coming in today to do the webcast with us. Jeanette Brown is currently a senior scientist at the University of Connecticut in the Department of Chemical Materials and Biomolecular Engineering. Jeanette?
Well, welcome all. This is the 4th in a series of webcasts this year, and this is the last for this year. So I'm looking forward to hearing your questions later on in this webcast. So today we're going to look at some definitions initially. We're going to describe the activated sludge process, talk about process control, and also troubleshooting. So first, some definitions that we're going to use throughout this webcast. The first is heterotrophic. Heterotrophic organisms are organisms that derive carbon for cell growth and energy from organic compounds. I like to describe heterotrophic organisms as us. And you'll see that explanation, why that explanation holds in just a little while. But just briefly, we use carbon for cell growth, and we get our energy from organic compounds. And we'll go into that a little bit more later. Autotrophic organisms derive cell growth from carbon dioxide, so they use inorganic forms of carbon. So they're a little bit different in their behavior. And those are organisms that exist in the bioreactors along with the heterotrophic organisms, and they're responsible for nitrification, which really occurs in most activated sludge wastewater treatment plants. Aerobic, as all of you know, it means that we have oxygen, dissolved oxygen in the water. And we're going to say that an aerobic tank really has about 2 milligrams per liter of dissolved oxygen. And that can vary from one plant to the next. SRT we'll use a lot, and we're going to talk quite a bit more later on in this webcast, but just briefly, it's the average time suspended solids are retained in the biological waste treatment system. And its counterpart, F on M, or food to microorganism ratio, and that's the loading rate on our system expressed as pounds of BOD5 per pound of mixed liquor volatile suspended solids per day, or kilograms of BOD5 per kilogram of mixed liquor volatile suspended solids per day. So when we look at a wastewater treatment plant, what we're going to be concentrating on today is that portion that's outlined in red. And when we talk about the activated sludge process, we always not only talk about the aeration tank or the biological reactor, but also the secondary clarifier. Those are coupled together and integral to one another, and they make up the activated sludge process. As you can see from this diagram, if you have primary clarifiers, the primary effluent is what enters the biological system. So when we look at making calculations around the activated sludge process, if you have primary clarifiers, you always use the parameters associated with the primary effluent. If you don't have primary clarifiers, then you would use influent characteristics. So secondary treatment is biological wastewater treatment, and it removes at least 85% of BOD in suspended solids. If you think about a typical NPDES permit, which was mandated under the Clean Water Act of 1972, mandated secondary treatment, which said 85% removal of BOD and suspended solids, and biological treatment meets that. It also stated less than or equal to 30 milligrams per liter of BOD and suspended solids. There are two types of secondary treatment. Biofilms, also called attached growth or fixed film, typically trickling filters and rotating biological contactors, and then suspended growth, which is the activated sludge process, which is what we're going to be concentrating on in this webcast. So this year is a very important year for the activated sludge process because it's 100 years old. In 1913, two researchers, Clark and Gage, at the Lawrence Experimental Station in Massachusetts, found that if you aerated sewage, you achieved a clarified sewage and a reduction of nitrogen. Very interesting results. They published those results in a report to the Massachusetts State Board of Health, and that was in 1913, 100 years ago. In 1914, two British researchers, Arden and Lockett, actually then took the concepts from Clark and Gage, and what they added was a recycled stream, and they patented this process. And in a publication in 1914, they first used the term activated sludge. The photograph that you see is the original first full-scale activated sludge plant, and that's in Davelhoom Sewage Works in Manchester, England, and it is still a functioning wastewater treatment plant. When we look at the activated sludge process, you can classify it according to the loading rate, and it could be expressed as a volumetric loading, or it can have something to do with the SRT, either a very short or a very long one, or food to microorganism ratio, a very low one or a very high one. And they're classified as high rate, conventional, or low rate, depending on these things such as SRT, food to microorganism ratio, and volumetric loading. We're going to be concentrating on a conventional activated sludge process. Typically, a conventional system will remove BODs between 85 and 95%, and actually you can see it even higher, close to 99% of BOD removal in a well-designed and a well-functioning conventional activated sludge process. For most of them, the mixed liquor suspended solids concentration is between 1,000 and 3,000 milligrams per liter. But I've seen plants operating up to as high as 5,000 milligrams per liter. Typically, they'll have an SRT between 3 and 15 days, although normally for BOD removal, you see it at the lower end, 3, 4, 5, 6 days. And F on M ratios between 0.2 and 0.4 pounds per pound or kilograms per kilogram. So for an activated sludge plant, we're going to need a biological reactor, aeration tank. It could be single or it could be multiple units. We need a source of that aeration because we need to have oxygen and mixing. We need a way of separating out solids. So we have clarifiers, secondary settling tanks. We need a collection and delivery mechanism for the return activated sludge. And we need a means of removing excess solids from the system. So here's a basic activated sludge process. We have our BOD5 coming in with either our effluent, our influent, or our primary effluent. We have our biological reactor, which is aerated, so we have oxygen. We have our return activated sludge, providing our microorganisms, and then we have a waste stream so that we can control the amount of microorganisms within the process. Just a reminder on biochemical oxygen demand. So biochemical oxygen demand is made up of two different aspects. One is the oxygen demand by the carbonaceous compounds, by the organic compounds, and one, the nitrogenous oxygen demand made up of nitrogenous compounds. The two of them together form total BOD. Some states write their permits with total BOD. Some states write their permits with CBOD, just the carbonaceous portion. And in order to get CBOD, what you do is you add an inhibitory chemical into the bottles. It inhibits nitrification, so you just get your CBOD. So just recall now that total BOD is made up of these two factors. So the activated sludge process will remove carbonaceous BOD and also removes nitrogenous BOD. Most activated sludge treatment plants will do those processes simultaneously. The carbonaceous BOD utilizes the heterotrophic organisms. The nitrification, the nitrogenous BOD, uses those autotrophic organisms, and it happens simultaneously. Some treatment plants don't want to nitrify, so they can operate their plant so it doesn't. But for the most part, a typical activated sludge plant will nitrify, so you're satisfying that nitrogenous oxygen demand. The design of an activated sludge plant is based on the length of time the solids are kept within the process, the SRT. The amount of food that's provided to the bacteria, this is the F on M ratio, and the hydraulic retention time. The hydraulic retention time is, for example, analogous to the detention time that you would calculate in a clarifier or a settling tank. So that differs from the SRT. The hydraulic retention time is really how long does a droplet of water remain in the system. With the solids retention time, it's a bit more complex. Our basic activated sludge process involves organic matter, and it's the carbon and energy source for cell growth. Carbon is converted to cell tissue, water, and oxidized products, mainly carbon dioxide. And we call the contents of our aeration tank mixed liquor suspended solids, with the volatile portion of that being mixed liquor volatile suspended solids. As I mentioned earlier, heterotrophic organisms are very much like us, and it's a good way to remember what they do. We eat organic matter, which contains carbon. That's our energy source and allows us to grow cells. And when we respire carbon dioxide and water vapor. Very similar to our metabolism are the heterotrophic organisms. The activated sludge process is really a big biochemical factory. It is amazing when you think of everything that's going on within that biological reactor and the various populations of organisms that we have within that system. We have bacteria, we have fungi, we have protozoa, we have rotifers, we have nematodes. And bacteria are really the significant organisms for consuming the organic matter. So those are the ones that are really doing the work within these biological systems. So the predominant species of microorganisms depend on a lot of things. What are the characteristics of the influent wastewater? What are the environmental conditions? What do I mean by environmental conditions? I mean pH of the water. I mean temperature and dissolved oxygen. That's the environment in which these organisms are living. So that's what I mean by environmental conditions. How's our process designed? Impacts our microorganisms, and how we operate our treatment plant. Many treatment plants can be designed identically and be in a different community, and the plant's going to operate differently, and you'll see different population dynamics of these various organisms, because really it depends a lot on these characteristics of the influent wastewater. In order to really run a very successful process, we want to cultivate that biological community, those organisms that will remove and consume our waste material, that will flocculate together, that will settle well to produce this concentrated solids that we're going to recycle to the head of the plant, to the head of the bioreactors as our source of microorganisms. And really, as important and more important is that it produces a clear effluent, because what we're trying to achieve is not only meeting our permit, but really doing what's right for the environment, protecting the water quality. So there's really two general types of microorganisms. There's what we call flock formers, and then there are filament formers. Flock formers clump together. They sort of excrete kind of like a sticky substance from their cells, and those allow one to stick to the other, and this forms this gelatinous flock, which is heavy and which will settle to the bottom of a secondary settling tank, and so that we can remove them from the system, have a nice clear effluent. And then we have filament formers, and they're stringy kind of thread-like structures. If any of you have seen them under a microscope, they look like hairs. A lot of them are lightweight, and they don't settle well. Now, you need some filaments in order to form this matrix that allows the gelatinous flock to settle well within a secondary clarifier. But you don't want a lot of filaments. And we'll talk more about filaments in just a little while. As I mentioned earlier, we use heterotrophic bacteria for carbonaceous BOD removal. So we can look at this formula here. We show organic matter, which is carbon. We have oxygen. We have nutrients, because these organisms need nutrients. And we have our microorganisms. C2H7O2N is the formula that's used to represent microorganisms. Sometimes you'll see this formula with phosphorus added. So because the cells do contain a little bit of phosphorus, a lot less than the rest of these. So it contains carbon, hydrogen, oxygen, and nitrogen. So what happens is now we produce new cells because we've gained energy from the organic matter, and we breathe out, the organisms breathe out, they respire carbon dioxide and water. I like to look at these processes with these box diagrams because it seems to be easier to understand. So in the box, which is our bioreactor, our aeration tanks, we have our bacteria, we have our input of oxygen, our input of nutrients, because like us, these bacteria need their vitamins and minerals. We have our food coming in, our organic compounds, we have our new cells, and we have our carbon dioxide and water. As I mentioned earlier, in most activated sludge plants, you'll also get nitrification. Nitrification is the conversion of ammonia to nitrite and nitrate. Many of you will have ammonia limits in your permit. A lot of permits say you can't discharge greater than 2 milligrams per liter of ammonia. The reason is that ammonia is toxic to many aquatic organisms. So nitrification is very good in that respect because we get rid of toxic ammonia and form non-toxic nitrite and nitrate. Now, that should not be confused with nitrogen removal because we still have nitrogen that's being discharged to our aquatic environments, but it does get rid of the toxicity of ammonia. So in this case, with nitrification, these are autotrophic organisms. So here's our autotrophic bacteria living in concert with our heterotrophic bacteria. They live in an aerobic environment. There's our oxygen. They need the nutrients. They use inorganic compounds. Remember, heterotrophics give off carbon dioxide, and these autotrophs are using the carbon dioxide to make new cells, and their byproducts are nitrite and nitrate. So when you picture an activated sludge plant and you think about looking into that bioreactor, into those aeration tanks, if we couldn't separate the solids from the liquids, then we wouldn't be doing anything to protect the environment. So an important feature of the activated sludge microbial population is its ability to separate by gravity. So we transfer the material from the biological reactors into our settling tanks, and because we have these flock formers and form these heavier particles, they're able to settle. So we get this settling action by selecting the cultures that settle the best. And we select these cultures by the environmental conditions we give them, primarily the amount of oxygen and how we recycle the sludge. Recycling is really important from our secondary clarifiers. And also operating the process under loading conditions that will select for a particular flocculent culture. So all of those, when your treatment plant is designed, all of these are taken into consideration and are part of the operations manual and are part of the equipment that we're given in order to operate the treatment plant. So now let's look at process control. So with process control, it is our responsibility to ensure that there's sufficient nutrients and food. We need to keep a balanced population of bacteria and protozoa. We need to provide sufficient oxygen for these organisms. And we need to provide mixing. So where do the food and nutrients come from? They come from the incoming wastewater. The food is in the form of BOD, and the nutrients are the nitrogen, phosphorus, and trace minerals that are part of the wastewater stream. There are actually treatment plants that have influent wastewaters that are deficient in nitrogen and phosphorus. So in order to make the process work, they actually have to add nitrogen and or phosphorus so that the microorganisms can reproduce and grow. As a general rule, for every 100 parts of BOD, you need 5 parts of nitrogen and 1 part of phosphorus. As you recall, the cells are made of carbon, hydrogen, oxygen, nitrogen, and as I mentioned, some phosphorus. We keep our balanced population by the return activated sludge, the RAS. That's the source of microorganisms to the aeration tanks, and typically what we do is return 30 to 50% of influent Q. We usually have pumps that will allow us to return a lot more than that, because designers provide typically 100% recycle rates, but we normally operate in the 30 to 50% rate, at least at most treatment plants. In order to keep the balanced population, we have to waste some of the material to remove any excess organisms. If we did not waste, then what would happen is there would be too big of a population of microorganisms for the amount of food that was available and the amount of oxygen that was available, and the process would fail. The organisms would starve to death, and the process would no longer function as designed. We need oxygen and mixing. Well, that's usually provided by the aeration devices. So when you design a biological reactor like this, you ensure that there's sufficient energy in your mechanical devices or your diffused air system that provide both mixing and aeration. The typical kinds of devices that we use are mechanical aerators. Many of them are at least 2-speed, so you can turn them up or down depending on what your needs are. Or diffused air, either fine bubble or coarse bubble, although typically it will be fine bubble. Fine bubble has a greater oxygen transfer efficiency. And what that means is that there's a lot more surface area available, so the transfer from the air to the water, it can be done much more efficiently, and the organisms can use the oxygen. Just as an aside, because so many of us are concerned about the high energy costs associated with operating our wastewater treatment plants, aeration is the biggest consumer of power in the wastewater treatment plant and represents at least 50% of the total power demand for treatment. So as you look to new aeration equipment, it's really important to look at designs that meet the mixing requirement and the oxygen requirement, but at the lowest possible cost. And there's now a lot of new technologies on the market that really allow us to optimize for the most efficient energy costs. So as we look at process control, what are the key parameters that we have to look at? Well, mixed liquor suspended solids and mixed liquor volatile suspended solids. Our solids retention time, which is also called MCRT, mean cell residence time. I use SRT. Food to microorganism ratio, F to M. Sludge volume index, SVI. Our return activated sludge rate, and our waste activated sludge rate, and dissolved oxygen. So what is mixed liquor suspended solids? Well, it's the concentration of suspended solids that's in the activated sludge mixed liquor. We measure that. Most treatment plants measure it on a daily basis because it's important in all of our process control calculations, and it really gives us an idea if we're in a stable operation. We express the results in milligrams per liter. What you do is you filter a sample, you dry these solids, and it's a combination of weighing them and re-weighing them. Typically 1,500 to 3,500, 1,000 on the low end. On the high end, perhaps as high as 5,000 milligrams per liter. But it's very plant specific. What might be good for you might not be good for someone else. So you might run at 1,200 milligrams per liter, and your friend who runs another treatment plant might be operating at 4,000 milligrams per liter. Like anything else with wastewater, it is very plant specific. One nice thing is it can be measured in situ now, which means you could actually put an instrument within your bioreactors and get a continuous readout of your mixed liquor suspended solids. And they're really quite accurate. And it's very good information. It's interesting to see how it varies. And it can alert you of a problem before you actually see a problem. Mixed liquor volatile suspended solids, that's the fraction of the suspended solids in activated sludge mixed liquor. It can be driven off by combustion at 550 degrees Celsius. You normally do it in a muffle furnace. And so it's really all of the volatile aspects of the mixed liquor. We use it to indicate the concentration of microorganisms available for biological oxidation. So it becomes an indicator to us of how many microorganisms we have within the system. It's not an exact measurement of it because what happens in this test is we're measuring any volatile material. So dead cells that are no longer working our process will also show up as mixed liquor volatile suspended solids. But it's a good and close approximation and gives us the information that we need to manage and control our treatment plants. So solids retention time is the same thing as mean cell residence time, is the same thing as sludge age. These terms we can use interchangeably. Depends on what your favorite term is. Mine happens to be SRT, so I always use SRT. But they all describe how long solids remain within your system. And remember, the system is not only the biological reactor, but it's also the clarifier. We have to think of those two tanks as the same unit process. So the solids retention time is dependent on the growth rate of the organisms, how quickly or slowly they're growing. And we use it as not only as a process control parameter, but as a design parameter. When you go to design a treatment plant, you will set a target SRT. And in fact, I'm sure if you look at your design drawings or your design manual, you will see what your target SRT is. So how do we calculate SRT? Well, in words, it's the solids under aeration, so the mass of solids, the pounds, the kilograms of solids that are within your bioreactors. So that's what's contained in that system divided by the solids leaving the system. So think about what I mean by solids leaving the system. Where do the solids leave the system? Well, they leave it in waste-activated sludge, and they also leave it in our effluent. And hopefully the effluent is very, very minimal in solids, but that's the other place where they leave the system. So it's the solids under aeration divided by what's leaving our system. If we're simply doing VOD removal, most plants will operate with a 3 to 5 day SRT. Again, it's very plant specific, and it depends on really your influent characteristics. If you're going to do nitrogen removal, primarily nitrification, then you want to be greater than 6 days. For the SRT calculation, if you have a significant blanket in your secondary clarifiers, then when you do the calculation, these solids need to be taken into account. But since you don't really want to carry a blanket in the secondary clarifiers, in the examples that I'll show you for calculations, I will not include them in the calculation. So first, we'll look at this with US units. So our solids under aeration are calculated by the volume of the aeration tank times our conversion factor, and that's in million gallons, times our conversion factor, which is 8.34 pounds per million gallons per milligram per liter, times our mixed liquor suspended solids in milligrams per liter. And our solids leaving the system is our waste flow in million gallons per day times our conversion factor of 8.34 pounds per million gallons per milligram per liter times the concentration of our waste activated sludge in milligrams per liter. So that's the waste activated, that's the mass of waste activated sludge that's leaving the system. And now we're going to add to that the mass, of solids that are going out with our effluent. So that's our plant flow in million gallons per day times our conversion factor of 8.34 times our effluent suspended solids concentration. So if we put them together, it's solids under aeration, which is this first calculation, divided by solids leaving the system, which is this portion of the calculation. If we look at it in SI units or metric units, then the solids under aeration is the volume of the tanks in cubic meters per day times our mixed liquor suspended solids in grams per cubic meter. Now, grams per cubic meter is identical to milligrams per liter, but we use it as grams per cubic meters so that as we cancel out the units, we're in the same type of units. And then we have to convert from grams to kilograms because we want the answer in kilograms. The solids leaving the system is going to be the waste flow in cubic meters per day, the concentration in grams per cubic meter, our conversion to kilograms, plus our plant flow times our effluent suspended solids times our conversion to kilograms. And again, we put it together the same way. Solids under aeration divided by solids leaving the system. So let's work through an example. If we have a treatment plant that has an aerator volume of 1.4 million gallons, that's equivalent to 5,300 cubic meters. Our plant flow is 3.1 million gallons per day, which is 11,735 cubic meters per day. Our mixed liquor concentration is 2,650. Our waste flow is 70,000 gallons per day, which is equal to 265 cubic meters per day. Our effluent suspended solids is 20 milligrams per liter, and our waste activated sludge concentration is equal to our RAS concentration at 5,960 milligrams per liter. Most treatment plants, the waste, you waste from the RAS lines, so the concentrations are going to be similar. Some plants waste mixed liquor, and in that case you would use the mixed liquor suspended solids concentration. So here's a worked example using those numbers. We have our 1.4 million gallons times 8.34 times 2,650. The million gallons cancels out, the milligrams per liter cancel out, and we're left with pounds. So the number of pounds under aeration, 30,941 pounds. The solids leaving the system, we said 70,000 gallons, but we want that in million gallons, which is 0.07 million gallons, times 8.34 times 5,960, plus our plant flow at 3.1 million gallons times 8.34 times 20 milligrams per liter, which is 3,997 pounds per day. So it's solids under aeration divided by solids leaving the process, so we have an SRT of 7.7 days. If we look at that same calculation using SI units, we have a volume of 5,300 cubic meters times our concentration of 2,650 grams per cubic meter. We divide that by 1,000 and we get 14,045 kilograms. Cubic meters cancel out, grams cancel out, and we're left with kilograms. The solids leaving the system, our waste flow is 265 cubic meters per day. Our concentration 5,960. We divide that by 1,000, plus our plant flow at 11,735 cubic meters per day times 20 grams per cubic meters, and we get 1,814 kilograms per day. So we divide solids under aeration by solids leaving, and we get 7.7 days. Another process control calculation is our food to microorganism ratio. It's the mass of food entering the reactors in either pounds or kilograms of BOD. And again, if you have primary clarifiers, it's the concentration in your primary effluent. The microorganisms, the mass of microorganisms is within the biological reactors. And this time, we're looking at the mixed liquor volatile suspended solids. So in the SRT, we used mixed liquor suspended solids. In the F on M ratio, we're going to just be looking at the volatile portion of that, which is typically about 80% of the mixed liquor suspended solids. So here's our calculation in US units. Our food is our plant flow in million gallons a day times our conversion factor, 8.3 times our BOD in milligrams per liter. And our microorganisms are our volume of our bioreactor in million gallons times 8.34 times mixed liquor volatile suspended solids. We divide the food by the microorganisms. And here's a worked example. We're using a mixed liquor suspended solids of 3,000 milligrams per liter, 82% volatile in this example. We have our influent flow of 16.5 million gallons a day. The volume of our bioreactor is 7.5 million gallons. Our primary effluent BOD is 135 milligrams per liter. So in calculating our food to microorganism ratio, it's our plant flow, 16.5 times 8.34 times 135 milligrams per liter divided by 7.5 times 8.34 times 3,000, which is our mixed liquor suspended solids. But remember, we want volatile suspended solids, so we have to multiply that by 0.82, 82%. If you look at this, we can cross out these. This cancels this, so you don't even have to multiply by 8.34 in either the top or the bottom. And we get an F on M ratio of about 0.12. In SI units, it's basically the same calculation, except now the flow is in cubic meters per day. The concentration is in grams per cubic meter, and again, our conversion to kilograms. So we still have our 3,000. We've converted now our plant flow, which was which we've converted to the metric system, which is 62,460 cubic meters per day, times our concentration of primary effluent BOD, which is 135 grams per cubic meter, converting to kilograms, and we're dividing it by the volume of our bioreactors converted to metric, which is 28,391 cubic meters times 3,000 times 0.82, again 82% volatile, converting that to kilograms, and we end up with an F on M of 0.12. Another very useful process control parameter is sludge volume index, or SVI. And this is measured in the laboratory. You take a graduated cylinder, you put your mixed liquor suspended solids in it, and you allow it to sit quiescently and settle. At 30 minutes, you look at how much it settled. And in this example, its settled volume is 210 milliliters. The calculation is SVI is equal to milliliters divided by mixed liquor suspended solids in grams. So in this example, we have a settled volume of 210 milliliters, and we're using a mixed liquor suspended solids concentration of 2,200 milligrams, which is 2.2 grams. And so when we divide 210 by 2.2, we get 95. Typically, at most treatment plants, you would want to be between 80 and 150. But like all other things, I have been to treatment plants that are running at SVIs of 250 or 300 and still getting excellent effluent quality. So again, like everything else, this is plant specific. But you should know what your target SVI is, because that's going to tell you how well your clarifiers are performing, because basically this test is mimicking what is occurring in your secondary clarifiers. So the RAS is the source of microorganisms, and the microorganisms use the food, the BOD. And as I showed you in the block diagrams, when they use the food, they reproduce themselves. So for every pound or kilogram of BOD used, we get about half of a pound to about 0.6 of a pound or a kilogram of new cells. The term we use for this is cell yield. Sometimes you'll see cell yields lower, like 0.4. So again, the cell yield is going to be plant specific. When a plant is designed, we use a theoretical cell yield, and then we can calculate the actual or observed cell yield within your wastewater treatment plant, and it's something that you can calculate. But because we're generating these new cells, we need to remove the excess cells. And we do that through our waste-activated sludge. So we always ask ourselves the question, well, how much should I waste? How much should I return? Well, we base that on mixed liquor concentration. What's our target mixed liquor concentration? What's our target F on M ratio? What's our target SRT? What are we trying to achieve within our plant? As I mentioned earlier, typically the RAS is 30 to 50% of the influent cube. Could be higher, might be lower. As I said, designers generally give us the capability of 100% recycle. That gives us redundancy. One of the things that you have to be very careful of is if you raise the return rate past a particular point, then the secondary clarifiers can fail. In a little while, we're going to be looking at solids loading rates on the clarifiers, and you'll see how the return activated sludge rate impacts the solids loading rate on the clarifiers. We can calculate how much to waste by rearranging the SRT formula and solving for waste-activated sludge. So here's our SRT formula. We said the pounds, the mass, the pounds or kilograms of solids in the biological system divided by the mass of the waste and the mass of the effluent. So we can write it in words like this and rearrange it. This is through simple algebra. Waste-activated sludge is equal to the solids in the biological system divided by the SRT minus the suspended solids that are leaving in the effluent. So if we look at this calculation now, so if we do it in the U.S. system, waste-activated sludge in million gallons per day is the pounds, the mass of waste-activated sludge, divided by 8.34 times the concentration of waste-activated sludge. If we do it in metric system, we want the result in cubic meters per day. So it's the mass of waste in kilograms divided by the flow in grams per cubic meters, and then again conversion from grams to kilograms. And one of the things that we really want to know is what's the volume of that? How long is it going to take us to waste? How many minutes do we have to operate our pump? So the next series of examples is going to show you that. So let's say that our waste-activated sludge that we have 6,774 pounds per day. So that's divided by 8.34, and if we have a concentration of 8,600 milligrams per liter, we end up with 0.094 million gallons per day, which is 94,000 gallons per day. Let's say our pump is a 250 gallon per minute pump. So we know in a given day we have to pump 94,000 divided by 250 gallons per minute, which is 376 minutes or 6.2 hours. So we would have to run this pump for 6.2 hours every day to remove the amount of waste material that we need to. This is the calculation that shows how we calculated the 6,744 pounds. So by rearranging the SRT calculation, here's our mass under aeration minus what's leaving the system divided by our 10-day SRT. If we look at calculating the pumping rate using metric units, SI units, let's say we have to remove 3,073 kilograms per day, then it's 3,073 kilograms divided by 8,600 grams per cubic meter. That's our concentration of our waste-activated sludge converted to kilograms. And we're saying we need to get rid of 357 cubic meters per day. That's the flow. And if our pump rate is 0.95 cubic meters per minute, so we divide our 357 cubic meters by our pump capacity, and we find 376 minutes or 6.2 hours. So now let's look at microbiology. We said that we have a big microbiological and biochemical factory. We have indicator organisms that we use all the time because they are easy to see under a microscope. Bacteria are a lot harder, and so with simple microscopes we can see amoebas and flagellates, motile ciliates, stalk ciliates, rotifers, and nematodes. And they all tell us different things. So for example, if amoebas and flagellates predominate, we have a young sludge. If we see mostly ciliates with some amoebas, flagellates, and a little bit of rotifers, we probably have a sludge that's indicating that our plant is well balanced and is giving us optimum performance. If we see a lot of rotifers and nematodes, we have an old sludge. And so our process may be failing. So let's see what some of these look like. So here's our free-swimming and crawling ciliates and protozoa. So you want to see these. These are easy to characterize under a microscope. The little dots in the background on this slide are bacteria. These are stalk ciliates, You can see the cilia, the little hair-like structures on them. These are some more stalk ciliates. They're really quite pretty to see under the microscope. In these particular micrographs, they've been stained so they can stand out. Here's our rotifers. This is a drawing of one, and these are actual rotifers seen under a microscope. Here's our filaments. We really don't like seeing them. This one especially, which is Nocardia, and we'll talk a bit more about Nocardia a little bit later in this webcast. And these are nematodes, and they're really not the prettiest things to see under the microscope, and they're very, very large. Here's some of your activated sludge flock in here, and you can see how large these nematodes are relative to the sludge flock. And they indicate a very old sludge. And these are some of my favorite organisms. These are water bears. And if you're doing nitrification within your aeration tanks, you'll tend to see water bears, and you can actually see little claws on the water bears, and they look very much like a bear. Okay, so let's look at control strategies now. How do we control our wastewater treatment plants? All operators have their preferred methods on how they decide how much solids to waste to maintain the optimum solids inventory. And that's really the key to this activated sludge process, is maintaining the optimum solids inventory, which gives us the population that does the right job for what we're looking for. What's right for one plant may not be right for another. And it's kind of fun to talk to other operators and compare what you do. The strategies that you could use for determining waste is looking at your F on M ratios, constant F on M, constant mixed liquor suspended solids concentration, or a constant solids retention time. So if you use F on M as a control strategy, what you do is you set a target F on M ratio, let's say, for example, 0.25. And then you try to maintain that by wasting. The problem with F on M control strategy is if your BOD, if your influent or primary effluent varies a lot, maybe because of intermittent side streams, it's a lot harder to control your plant using the F on M control strategy. Constant mixed liquor suspended solids, what you might do is set your target mixed liquor suspended solids at 2,500. So you will waste to always maintain that 2,500. But your sludge growth rate may change because of influent variations, either temperatures declining or increasing. But it is the easiest control strategy, and it's especially good for small treatment plants that don't have a lot of laboratory abilities. It's really the easiest way if you're a smaller treatment plant. And then SRT. And SRT is pretty much used at most treatment plants, especially larger treatment plants. And what you do is set a target SRT, and you really waste the same proportion of activated sludge inventory every day, regardless of the variations in the influent wastewater. So for example, if you set a target SRT of 10 days, every day you'll waste 10% of the mass of the mixed liquor suspended solids in your bioreactors. So if you have 100,000 pounds of mass of mixed liquor suspended solids, every day you would waste 10,000 pounds to maintain a 10-day SRT. SRT control is easier for operators to maintain. It gives operators more control on the process and more stability. But you really need to decide for yourself which one is easiest for you, which gives the best performance for your treatment plant, because the whole key is ensuring that you make permit, ensuring that you protect water quality. But you should be open to suggestions and changes. But the most important thing is to choose what you're comfortable with. So we talked earlier about the activated sludge and the advantage of the activated sludge with the ability to settle solids. Solid separation is critical. Clarifiers are part of the activated sludge process, as I mentioned. You always draw the boundaries around both the activated sludge tank, the aeration tank, and the clarifier. So as operators, you need to understand and manage clarifier performance so that you get optimum permit compliance, and that also you get a good quality return activated sludge, that it settles well, that is a good concentration. And so you have to know how RAS impacts clarifier performance. So there's 5 parameters that will have the most influence over the performance of a well-designed secondary clarifier. The mixed liquor suspended solids concentration, the flow to the clarifier, what your wastewater flow is, what your return activated sludge flow is, the surface area of the clarifier, and the settleability of the activated sludge. That's that SVI. So, and that's probably a critical, most critical importance, is keeping the SVI in your target range. Typically, secondary clarifiers are circular, but you do see rectangular ones. They have lower detention times than primary clarifiers, and that's because the solids that settle, the activated sludge, is biological sludge, and it decomposes fairly rapidly. And if it decomposes, you'll get gas bubbles rising to the surface. This happens a lot of times if you're nitrifying, only nitrifying in your bioreactors, and then you'll actually denitrify in your secondary clarifiers, especially if you carry a deep blanket where you have an area that's devoid of oxygen, and you'll get denitrification, and you'll see those bubbles rising to the surface, and lots of times you see clumps of solids coming to the surface, which can impact your effluent. With biological nutrient removal systems, you want to have overflow rates of about 600 gallons per day per square foot, as compared to just typical activated sludge, which is about 800. And your solids loading rate about 30 pounds per day per square foot for the activated sludge process, for only BOD removal. So surface overflow rates are important to calculate. They describe the hydraulic loading of your treatment, of your clarifiers. We use them in design, and we use it in process control. So the surface overflow rate is the plant flow in gallons per day divided by the surface area in square feet. Or in the SI system, it's your flow in cubic meters per day divided by your area in square meters. So if you're in the United States, your SOR is reported as gallons per day per square foot. And if you're outside of the United States using an SI system, it's cubic meters per square meter per day. So let's look at an example. We have an area of 7,000 square feet per unit, which is 650 square meters per unit. We have a flow of 5,500,000 gallons per day, which is 20,820 cubic meters per day. So we divide the 5,500,000 gallons by 7,000, and we get a surface overflow rate of 750 gallons per square foot per day. And in the SI system, it's 20,820 cubic meters per day divided by 650 square meters, or 32 cubic meters per square meter per day. Solids loading rate is a bit different in that we're looking at now the massive solids that are going into those clarifiers. In the surface overflow rate, we only use the plant flow. But in looking at the solids loading rate, we use a combination of the plant flow plus the return flow because we want the total mass of solids. So it's Q plus QR, or R, times our mixed liquor suspended solids. And in the U.S. system, times 8.34, because we're looking for the mass of solids. Again, we divide it by the surface area. In SI, it's going to be our flow in cubic meters per day plus our return flow in cubic meters per day times our mixed liquor suspended solids concentration converted to kilograms divided by the area in square meters. So let's look at an example. So we have a plant that has 18.2 million gallons per day, or 68,894 cubic meters per day. A return flow of 7.7 million gallons per day, or 29,148 cubic meters per day. Mixed liquor concentration of 3,350 milligrams per liter. A surface area of 39,978 square feet, which is 3,714 square meters. And if we take our plant flow plus our return flow, multiply it by our concentration, in the case of the U.S. by our conversion factor, divided by the area for, we get a solids loading in U.S. units of 18 pounds per day per square foot, and in metric units, 8.2 kilograms per day per square meter. So let's look at the tools that we have available for us for process control. There's 4 steps that we need to manage any process. We need to have the information associated with it. We need to look at those data and evaluate those data. And then we have to develop and implement a proper response. And then we have to go back and reevaluate to make sure that our response, that the response that we came up really did do its job. So the information that's available to us is like analytical data or runtime meters, visual information, a lot of miscellaneous facts. Information is only as good as the device used for analysis. So if your laboratory data is suspect, then you can't really make judgments on it. If your meters are not calibrated, you can't make process judgments based on that. So you need to be very careful with the instruments you use, that they're calibrated, with your analytical procedures, that they're done properly. A lot of the data that we get is numerical data. So you want to use graphs, you want to calculate mass balances, and use basic statistics. This is a graph of actual data. This is a 3-year data set. The blue is the average monthly influent BOD concentration. The red is the average monthly total suspended solids concentration. And you can see visually when you plot it, the variability in these 2 parameters. You wouldn't see that just by looking at a list of numbers. So plotting the data using graphs is is just very, very beneficial. A lot of times SCADA systems will generate the graphs. Certainly programs like Excel can easily generate graphs of all different kinds. And so that's what you really need is visual aspects to be able to really see the variabilities. And things will stand out to you. You know, for example, this low point on influent suspended solids. This is probably associated with a rain event where it dropped very, very low. So it gives you a tool to be able to visually make some judgments and then go back in other data to look at. Mass balances are scary to a lot of people, but they're relatively simple to do. You can do a simple mass balance where you can track what's happening to the solids throughout your treatment plant or to the BOD or other parameters. So in the remaining time, we're going to look at some troubleshooting and how to troubleshoot. So the first thing you need to do is gather information. And we need to, so in gathering the information, we need to have knowledge of our specific plant. We need to know what the waste constituents are. So in other words, what are the influent wastewater characteristics? And we need to look at the specific process that we're trying to troubleshoot. So how do we gather the information? Well, the very first thing you need to do is, do we really have a problem? Or did the laboratory give us bad information? So let's say the laboratory comes back with an effluent suspended solids that's way above permit, and yet you go out and look, and the effluent looks really good. Before you start making any changes, you want to verify that. Have another test taken. If there is a problem, when did you first see it? If you see solids carry over in the clarifier, when was it first observed? And did anybody do anything about it? Has someone already made a change? Because you don't want to make changes upon changes. If you're having a process upset, take a look at the biomass under the microscope, because those microorganisms are going to give you a lot of information very, very quickly. You can look at it and determine if there's a problem almost instantaneously. And of course, just being out by the aeration tanks, looking at the mixed liquor, smelling it, that will give you very, very good information once you understand what your normal plant is like. The other thing is, you know, was there something that was done within the plant that contributed to a problem? Was there a side stream that maybe should have been metered into the plant slowly but came in as a slug? So was it internal to the plant? Or was there something outside of the plant that was discharged into the plant? So you need to take a look at whether or not it's internal or it's external. For the laboratory, you want to make sure that you have a good quality assurance program. You want to make sure that you don't have chemical leaks in your system that's going into the process. You want to make sure that your bioreactor air delivery system is working well. You want to make sure that there's no other mechanical or electrical problems. So before you start making any kinds of changes, you need to gather the information associated with the problem. Was there a power outage? Did an RAS pump go down and it didn't restart automatically? You need to separate the symptoms from the problems. You want to talk to all of the operators, anybody that's observed what the problem is. Listen to them. Listen to their interpretation. But you want to be able to yourself interpret what they're saying. You want to treat the disease, not the symptom. So you want to look at the root cause of what's happening. Lots of times we're tempted to treat the symptom, but what you want to do is treat the disease. And sometimes things aren't always as they first appear, so you don't want to make a judgment right away. It's more important that you take your time, analyze the problem, make sure that everybody sees the problem the same way you do, and then start taking corrective action. To effectively troubleshoot, you've got to determine the probable cause of a problem, and then select one or more corrective measures to restore the process so that you have the least effect on the final effluent and hopefully at the lowest cost. However, you only want to make one corrective change at a time. In order to be able to troubleshoot, you need to have thorough knowledge of your plant's process. You need to understand it and be very, very familiar with it. You need to know what your influent characteristics are typically, what the plant flow rates are, how does the flow pattern change. You want to look at your design and actual loading parameters. Are you within that? Did you get a slug which has increased the load coming into the plant? What's the typical performance of the overall plant and each unit process? So you need to really, really be familiar with your plant and what the maintenance procedures are. So sometimes maintenance can cause us a problem, so you need to know what our maintenance procedures are. So when a problem arises, you need to find out, does it fit into one or more of these areas? Is it due to hydraulics? Is it due to a mechanical failure? Or is it due to a process upset? Or is it due to a combination of these? So what are hydraulic problems? Well, they're easy to detect because you get solid washout and secondary clarifiers typically. And it's typically from rainstorms. It's especially true if you have a combined sewer system, but in recent years with climate change, we're seeing more severe rainstorms, and so we're seeing plants that are in towns that have separate systems really spiking on their influent flows, causing really severe hydraulic problems through the system. You may have a problem where you had to take a tank out of service for emergency repairs, and that may be causing hydraulic overload on the downstream equipment. Mechanical problems can result in effluent violations, so they need to be, you really need to have high quality maintenance. You need to ensure that you have redundant equipment. So if an RAS pump goes down, you want to make sure you have a standby RAS pump, because otherwise you're going to build up sludge in your clarifier and your mixed liquor is going to drop in your bioreactors. So some of the problems that typically occur is problem with the collector mechanism on the clarifier. You can see them, sometimes they get overloaded. Sometimes debris will fall into them and it will catch the rake and will fail. Your return activated sludge pumps, sometimes your blowers will fail, or you'll have a problem with the mechanical aerator, or sometimes you'll see some of the headers with diffused air actually breaking and floating to the surface of the tank. So mechanical problems are pretty easy to solve, or at least identify. Process problems are a lot more challenging. We really have to be kind of forensic experts in analyzing process problems. One of the most important things is maintaining good records, because with good records, many times you see warning signs of an impending problem. You'll see your SVIs maybe starting to creep up. And this again is the value of graphing your data on a regular basis, because you'll start seeing something creeping up or going down. Maybe your influent characteristics are changing. Maybe you have a normal influent BOD of 250 milligrams per liter, and then all of a sudden they're jumping up to 350 or 400, and that can change your entire plant operation. So you need good records, and you need to look at those records and put them in a form that gives you the most information in the quickest possible time. You need to be familiar with the side streams. These side streams can include digester supernatant. It can include your filtrate or centrate from your filter presses or from your centrifuges. And if those change, they will have an impact on your treatment plant. You need to pay attention to dissolved oxygen concentrations. A number of years ago, a plant that I was working at, all of a sudden the dissolved oxygen started to plummet. And they put on all of the blowers that they had, and still the dissolved oxygen continued to drop. No matter how fast, how much air they were putting in there. And the mixed liquors started to drop off within a 20-hour period of time. And it turned out a toxic came into the plant, and this toxic affected the microorganisms. So paying attention to that dissolved oxygen concentration and the mixed liquor suspended solids gave the plant personnel an understanding of what was happening. You really need to have those plant records, and you really need to look at them on a daily basis in order to effectively troubleshoot your treatment plant. Microscopy, again, is an excellent way of troubleshooting the treatment plant because it's easy to do. It doesn't take a lot of expensive equipment. It doesn't take, there isn't a big learning curve on it. What you want to do is ensure you know what your microorganisms should look like when the plant is operating at optimum. Do you see mostly stocked ciliates? Do you see combinations where you have a lot of amoebas in there in the stock ciliates? Or maybe you have some rotifers in there under normal conditions. And then when you start looking at it again, the next day maybe you see some filaments creeping in, or you see some rotifers creeping in. That begins to tell you that there is a problem, and you could now start taking corrective action on that problem sooner before you may have a problem with your effluent quality. So to troubleshoot, we need a lot of skills. We really are forensic scientists. We need to have investigative thinking and a logical use of what we have available to us. You don't want to jump to judgment. So as you investigate things, you want to look at all of the data associated with it and then use the kinds of tools that we have in a logical way. And when troubleshooting, when taking corrective action, you don't want to make more than one change at a time because you need to know whether or not a change was effective. Multiple changes made all at once, you don't know which made the difference. So if you have a problem in the future, you don't know which one you should do. The activated sludge process is biological, so the responses are not quick to our frustration. It can take days or weeks before process improvement can be seen. Many times it's 2 to 3 times your SRT. So if you're running at a 10-day SRT, that could be 20 or 30 days before you really see the kinds of improvement that you want to see. It takes a huge amount of patience when you troubleshoot and try to make changes in a process. So successful troubleshooting, thorough knowledge of your process, thorough knowledge of your side streams, thorough knowledge of loading and design values, thorough knowledge of your maintenance procedures, of whether or not your ability to recognize abnormal conditions, what alternatives are available to us when trouble happens. Do we have spare pumps? Do we have a spare bioreactor, a spare aeration tank, where maybe we can put some of the mixed liquor temporarily while to prevent solids carryover in our clarifiers. And thorough knowledge of the industries that are discharging to the treatment plants, because sometimes an industry will have a problem, discharge something to us that's really harmful. Laboratory testing, incredibly important. You want to look at settleability tests, sludge volume index, mixed liquor respiration rate, OUR or specific OUR. This gives us a lot of information as to whether or not a toxic chemical came into the plant. Again, these are not difficult tests to do. We always want to look at dissolved oxygen, and we also want to monitor our sludge blanket within our clarifiers. Again, operating with a minimum blanket. This is a settleability test that is done in our laboratories. As I mentioned earlier, you put mixed liquor into a graduated cylinder and you let it settle. And you look at what's happening. If you have a nice clear effluent, clear supernatant, you have a good SVI, you know that your clarifiers are going to perform well. But if after 30 minutes you get a pretty good sludge, but after an hour or 2 hours, which is typical detention time in the clarifiers, if your solids start to float, you may have an effluent problem. If you don't get any settling at all, if you have a very dispersed block, then you have a problem within your plant. So the settleability test can give you good information, again, quickly. And using troubleshooting guides, this is from our WEF Manual of Practice, MOP 11, it will give you guidance on what corrective measures to take. So let's look at a few of the common operational problems. Foaming in the bioreactors, solids washout either through hydraulics or solids loading, and we'll look at some bulking. So lots of times we'll see a lot of white foam in our bioreactors. White foam tends to indicate a young sludge, so a sludge that has a low SRT, maybe a day or less. And lots of times it's found in treatment plants that are brand new. When you start up a treatment plant for the first time, lots of times you'll see a lot of this white billowy foam, and I've actually seen it blowing across roads adjacent to the treatment plant because the wind will just catch it. And that's because the mixed liquor suspended solids concentration is too low, which means that the food to microorganism ratio is too high. In other words, there's a whole lot of food there, but not enough microorganisms, and so you get this white foam. Some of it consists of detergents. Some of these are detergents in the wastewater. Others are detergents that organisms really excrete, or proteins that can't be converted to food by the bacteria that grow in the mixed liquor at these high F/M ratios. So some of the causes in a plant that's been running is with the RAS flow. So in the middle of the night, the RAS pump goes down, nobody notices it. The next morning your mixed liquor is 800 and you've got tons of white foam over the surface of the aeration tank. Somebody put on the waste activated sludge pump and didn't turn it off. Now you've wasted a lot more of the sludge, resulting in a very low mixed liquor suspended solids. Or you might get a toxic or an inhibitory material coming into the plant. And those are very difficult. They're very difficult to identify. They're difficult to track back to the source. Sometimes herbicides and pesticides can be really toxic to these systems. If you have a very low or a very high pH, or you don't have enough dissolved oxygen, or you don't have enough nutrients, you can also get this white billowy foam. And what you'll see is a lot of biomass in the secondary clarifier effluent. So some of the corrective measures that you can take: you want to make sure that your return activated sludge is flowing to the biological reactor and that it's flowing at the rate that you want. You want to ensure that the sludge blanket is in the lower quarter of the clarifier, between 1 and 3 feet from the bottom, or about 0.3 to 0.9 meters, preferably on the low end, 1 foot, 0.3 meters. You might want to stop wasting. If your mixed liquor concentration has dropped significantly, then stop wasting until it comes up to your target value, or your SRT comes up to your target value. One of the worst things that we see is brown foam. There's other causes for brown foam, but one of the causes typically is nocardia. And this photomicrograph shows the typical nocardia organism. Lots of times it's caused by operating at high solids retention times, although it's common at low solids retention times. And if you have trapped surfaces, or if you recycle the foam, then it just compounds the problem and it gets worse and worse. Nocardia foam is very difficult to eliminate. It's difficult to break with water sprays. It really is the consistency of chocolate mousse. And in fact, if you have a significant amount on the surface of your aeration tanks, it really represents a lot of solids and really ought to be taken into account in your SRT calculations. The other thing is it doesn't really respond to chemical antifoamants. It really, either they don't penetrate deeply enough through the foam, which is part of the problem because it's such a thick, viscous material. I've also tried chlorinating, spraying chlorine water on the surfaces of the foam, and it'll penetrate a little bit, and the surface will clear up the surface of the foam layer, but it won't penetrate deeply enough in many cases if it's very thick to be effective. You can chlorinate the return activated sludge. It doesn't totally eliminate nocardia, and the problem is that it'll affect the nocardia if the nocardia is outside of the flock. So if it's extending outside of the flock, you will see some effect by chlorination. But if it's inside of the flock protects it, so it'll just stay there and really continue to increase. You can increase wasting, but again, that has some limitations because the foam itself is not wasted with the waste-activated sludge, although some of the modern plants now actually have foam wasting systems, where at the end of the aeration tank, you'll have a foam overflow weir, and the foam can be wasted directly to thickening or dewatering equipment. And that really is very good, and it gets the foam out of the system, especially if you could put in some chlorine into that foam when it's containerized before it goes to the dewatering or thickening equipment. If the foam goes into, if you remove it from the, say for example from the surface of the clarifiers, it's usually going to go in with the sludge that might be going to your digesters, and it can create problems in the digesters. So this foam is a real problem. Some plants have horrible problems with it, others do not. Site-specific, sometimes there's a seasonality associated with it, and it's not that easy to get rid of. So what are some of the possible corrective actions? Well, if you can decrease the SRT, that sometimes helps. Not always, but it's something to try. You might try to figure out why you're getting filaments in general. So if we're not, let's now talk about other filamentous organisms, not just simply Nocardia. So why are we getting these filaments? Is something coming into the treatment plant that's causing some of these filamentous organisms to grow and to thrive? And other filaments like Betuatoa or Thiotrix, for example, really respond very well to chlorinating the return activated sludge. And you can really get rid of them fairly quickly by doing chlorination of the return activated sludge. But you want to try to get rid of the foam. That's probably one of the most important corrective actions you can take. So what happens if you're getting suspended solids carryover from your clarifiers? Well, you need to analyze it. Is it due to hydraulic overload? Did you exceed your surface overflow rate because of rainfall? In your distribution box, if you have more than one clarifier in your distribution box, are you getting equal flow to all of the clarifiers, or has something happened so most of the flow is going into one particular clarifier? And visually you can tell that right away just watching the volume of water that's coming over the weirs. Ensure that the weirs are level, because if the weirs are not level, you're going to get short-circuiting in that clarifier, which allows for density currents, which allows for resuspension of the solids that will go into the overflow. Solids overload will also affect your effluent quality from your clarifier. So again, as we talked earlier, you need to calculate that solids loading rate. Make sure it's within your design solids loading rate for your clarifiers. If not, it may turn out that you have a problem with your return rate, and you need to look at that. You may need to calibrate your pumps again. Or there might be, you might have increased your mixed liquor suspended solids trying to correct one problem without thinking about its impact on the solids loading rate. So we have different kind of bulking. Bulking is a problem within the clarifiers. The solids are not settling, so we're going to get poor effluent quality. So there's a filamentous bulking, and there's non-filamentous bulking. So first, we'll talk about filamentous bulking. So it can be caused by low dissolved oxygen concentrations in your reactors. There's a lot of low DO filaments that come in. If you have insufficient nutrients, you may get growth of filamentous organisms. Same thing with pH. If it's either too low or if it varies a great deal over a short period of time. Warm wastewater temperature tends to exacerbate the growth of filamentous organisms. If your organic load varies a great deal, either due to the way side streams come into your plant, the way industries come into your plant, or even if you have a lot of septic tanks that discharge to your plant. These varying organic loads can really cause filamentous growth. And if you have industrial waste that have really high VODs and low nutrients, that can be another cause of filamentous bulking. High influence sulfide concentrations. You get this organism Thiotrix. Whenever you see thio, it means that it has sulfur. So Thiotrix is caused when you've got a lot of sulfide. That could come from maybe too much anaerobic digester supernatant, but it can also come from if you have flat sewers in hot climates, you could produce a lot of hydrogen sulfide, and that can come in as a slug load into your treatment plant, or even an industrial load. Again, low F-on-M ratios, which might allow for the cardia. Or if you're recycling a lot of the filaments. You really want to try to get rid of the filaments through some control strategy. And as I mentioned earlier, Thiotrix, Vegetatos, some of the other filaments will respond well to chlorination of the return activated sludge. You do have to be careful when you chlorinate the return activated sludge because you don't want to kill the good organisms. So you don't want to use it for long periods of time, and you don't want to use high concentrations of chlorine. So if you're going to add chlorine, you want to find what's the good point to add it in. So you want to make sure that there's good mixing where the sludge is concentrated, like in your return activated sludge, and where wastewater concentration is at a minimum. You really want to attack the organisms in the most concentrated form. So a lot of treatment plants feed it into the return activated sludge line before it gets to the bioreactors. Typically the return activated sludge line. Sometimes you can put it in the biological reactor. You put it in just where the return activated sludge comes in. Sometimes you can put it into an installed side stream that kind of recirculates mixed liquor within the bioreactor. You want to look at the dose and the frequency at which the organisms are exposed to the chlorine. Those are the most important parameters. You want to adjust the dose so that the concentrations are lethal at the flock surface, but not within the flock. You don't want to kill the good organisms. So the chlorine dose is based on solids inventory in the process. And typically doses that you see are 1 to 10 grams per kilogram of mixed liquor volatile suspended solids per day, or about 1 to 10 pounds of chlorine per day per 1,000 pounds of mixed liquor volatile suspended solids. So the other kind of bulking we have is non-filamentous bulking. Sometimes this is caused by polysaccharides, and you can identify those under a microscope by staining your slide with India ink, and you'll see it's very easy to identify polysaccharides, and that's one cause of non-filamentous bulking. Improper organic loading, either too high or too low an F-on-M. You can see that F-on-M plays an important role in how well sludge will settle. Over-aeration can be a problem, and also toxics coming into the treatment plant. So if we look at our potential corrective actions, so the first thing you want to do is make sure that it's non-filamentous bulking. Then you want to check your F-on-M ratio to make sure it's in the target range. You'll see small dispersed floc, which are characteristic of a higher F on M. If the F on M is higher than normal by 10% or more, then you should decrease the wasting rate. And when you decrease it, you want to do it gradually, not all at once. A decrease in the F on M should be reflected by the disappearance of dispersed floc. So as the F on M starts to go down and the SRT starts to come up, then this dispersed floc should start to go away. And that can take 2 to 3 SRTs. And as I mentioned, if you have an SRT of 10 days, that could be 20 to 30 SRTs, 20 to 30 days. The other thing is if you have a lot of turbulence in your bioreactors, that can cause shearing of the floc and therefore non-filamentous bulking. Sometimes mechanical aerators can shear the floc because of high turbulence. Sometimes over-aeration. This would be dissolved oxygen concentrations greater than 4 milligrams per liter. So what you want to do is get your dissolved oxygen concentration down to 1.5 to 3 milligrams per liter. And toxics. Toxics coming into the plant will have effects and will affect the plant in many different ways, and they can affect it through bulking also. So to summarize today, really when we look at process control and troubleshooting in our treatment plants, you need to understand the process, the activated sludge process in general, and the activated sludge process specific to your plant. How does it work at your plant? You need good process control, so you need good information, good laboratory data, good instrumentation, well-maintained instruments, well-calibrated instruments, laboratory data with a good QA/QC procedure. Troubleshooting is complex. It takes a lot of time and a lot of skill. Always step back, think about the problem, gather as much information as you can about the problem. Before you start making any changes, make sure you've identified the problem correctly, and then make only one change at a time. So for more information on the activated sludge process, please refer to MOP 11, and we also have another manual of practice which is specific to the activated sludge process, and those will give you really good information, and we'll bring that up on the screen in just a second.
Yes, and I just wanted to mention as well, thank you very much, Jeanette, by the way. That was awesome. But I just wanted to mention that the slides have been updated a little bit, so I will be posting the updated slides on the FTP site by tomorrow.
Okay, so we will take a few questions. Let's see. So the first question, how to prevent denitrification in the clarifier? Part of it is not maintaining a thick blanket in that clarifier. You really want to work at a very small blanket, as I've mentioned, and so if you maintain a smaller blanket, it will help. If you are removing nitrogen, if you're required to remove nitrogen and do denitrification within your bioreactors, you want to optimize that process. If you don't want to nitrify, if you don't have to nitrify, then don't nitrify, and then you won't get denitrification. So those are a few things. Question about the ratio of BOD, nitrogen and phosphorus. It's 100 BOD to 5 nitrogen to 1 part phosphorus. Can you provide a few examples of new technologies to reduce aeration energy costs? Yeah, there's some new blowers on the market. They're called turbo blowers. They're much more energy efficient. They're low maintenance. So they, those are good ones to look at. The question for SRT calculation is the volume, including the volume of the clarifier. No, the only time you include anything to do with the clarifier is if you carry a lot of solids in the clarifier, and then you have to include the mass of the solids. So that would be the volume of the clarifier times the concentration of solids. But if you don't carry a real deep blanket in those clarifiers, then exclude the clarifier solids. What benefit is there from wasting wasting mixed liquor from the activated sludge plant rather than the clarifier? It's just easy to set up your controls for it. So if you're going to say do it based on a constant SRT, then you could calculate the mixed liquor suspended, the mass of mixed liquor suspended solids, and just automatically, if you want a 10-day SRT, just waste 10% of the mass of that mixed liquor suspended solids. It's just easier to do it that way. The only caveat is if you're going to thickening equipment, then the thickening equipment has to be sized for the increase in hydraulic loading, because there's going to be more water associated with the mixed liquor suspended solids than there would be with the typical waste activated sludge, because that is more concentrated. You know, your mixed liquor suspended solids might be 2,500 milligrams per liter. You return activated sludge might be, you know, 6, 7, 8, 9, 10,000 milligrams per liter. So you can't just waste mixed liquor suspended solids if you're going to thickening equipment that isn't sized for that increased hydraulic loading. Please help settle an argument. Our plant has microstrainers for tertiary treatment. When our plant calculates SRT, they use final clarifier effluent solids as the solids leaving the plant. Yes, for SRT, that's what you would want to use, because you want to look at the clarifier and the bioreactor as a unit. The microstrainers come on after, say, the activated sludge process. So you would use the clarifier effluent solids. Let's see. How is SRT controlled? You control it through waste-activated sludge. What are the conditions for the growth of Nocardia? As I mentioned, it could be higher SRTs, but I've seen it at low SRTs. There's just all sorts of different causes and conditions for it. But really, you see plants that are running at higher SRTs, you see more Nocardia problems. What are my thoughts about deammonification? Deammonification is a process that's used typically for nitrification. You go from ammonia to nitrite to nitrate, and then for denitrification you go from nitrate to nitrite to nitrogen gas. Deammonification is a way of shunting that, so it uses less oxygen and less carbon. Right now it's been proven on side streams for small flows with high ammonia concentrations. There's work being done now on full stream plants. I think it will be a while before we'll have sufficient data to be able to make a judgment on full stream plants. And I think we're going to end it there because it's time.
Of course. Thank you so much, Jeanette. Thank you for all 4 webcasts that you've done this year. If anyone's interested in viewing the recordings, this webcast recording and the 3 others that Jeanette did this year are posted online, wef.org/webcasts, and you just go to the individual webcast page. We have 2 more webcasts coming up in July, so I want to thank everyone for participating today and have a great day.